Welcome to a deep dive into something kind of mind-bending. We're talking about the electric universe.
Yeah.
And, most of us, when we think about space, we think about stars and planets and like the vast emptiness out there. We usually think, oh yeah, it's buzzing with electricity.
Right.
So we're going to dive into this whole model of the universe that puts electricity front and center.
It's true. I mean, we're kind of biased by our experience here on Earth. Like, down here, it's mostly gravity and the stuff we can see and touch.
Right, makes sense.
But when you look at the universe as a whole, that kind of matter, it's actually not the main course.
Oh, really?
Yeah. It's more like a side dish. The vast majority of the universe is something else entirely. It's this stuff called plasma.
Okay, plasma. So break that down for us. What exactly are we talking about? Give us the layman's terms.
All right, so imagine like the air we breathe, but supercharged, like really amped up with energy. So much so that the atoms are actually stripped of some of their electrons.
Oh, wow.
Yeah, and you end up with this sea of charged particles. And that, my friend, is plasma.
Okay.
And the sea, this plasma sea, it does something really cool. It conducts electricity. It forms these currents, these filaments, almost like
Like cosmic power lines.
yes, like
Yeah.
cosmic power lines threading their way through space.
I like the sound of that,
Yeah.
cosmic power lines. So how do these cosmic power lines, how do they factor into this whole electric universe idea?
Well, that's where things get really interesting. The electric universe model, it suggests that these electrical forces, these currents flowing through the plasma, they play a much larger role in shaping the universe than we ever thought.
It's like I was reading H.P. Lovecraft the other day, and he has this whole thing about how, like, if we ever truly understood the interconnectedness of the universe, it would drive us mad.
Oh, wow.
And it kind of feels like that's what this electric universe is trying to do, like connect all these dots in this new way.
It definitely makes you think about things differently.
For sure.
I mean, think about auroras, right? Those incredible light shows we see here on Earth.
Oh, yeah, absolutely stunning.
Right. They're like a perfect example of how space isn't just this empty vacuum.
It's teeming with all this stuff.
Exactly.
Yeah.
Charged particles interacting with Earth's magnetic field, creating those beautiful, shimmering curtains of light.
It's like a giant neon sign, right?
Yeah.
Reminding us that the universe is a much more electrically active place than we tend to imagine.
Mm.
But auroras are tiny, right?
Yeah.
Compared to like galaxies.
Right?
So how does this model, how does the electric universe explain those massive structures, those galaxies?
So that's where the concept of redshift and the work of this guy, Halton Arb, comes into play.
Okay.
Now, you might be wondering, why should I care about redshift?
Why?
Because it's been like the cornerstone of how we measure the universe's expansion for like the past century.
Okay.
But Arp's observations, they kind of threw a wrench in the works.
Oh, really?
Yeah.
Okay, so back up a bit. What is redshift? For those of us who haven't been, like, studying space since we were kids.
Right, of course. So redshift, imagine the sound of a car, right? Like a car speeding away from you.
Okay.
The pitch gets lower, right?
Yeah.
That's the Doppler effect. Redshift is similar, but with light. So the farther a galaxy is from us, the more its light stretches, it shifts towards the red end of the spectrum.
Okay.
And astronomers have used this redshift to calculate distances, and it's how we got this whole idea of an expanding universe.
Okay, that makes sense. But you said this guy, Arp, his observations challenged this whole idea. How so?
So Arp was looking at galaxies that, based on their redshift, should have been incredibly far apart, like millions of light years even. But when he observed them closely, he found something astonishing.
What's that?
They were physically connected, like literally side by side.
Whoa, that's crazy. So are you saying that redshift might not be a reliable indicator of distance after all?
That's one of the core arguments of the electric universe proponents. They look at Arp's findings and they see a universe that might be a lot more compact and interconnected than we think.
Okay.
A universe where electricity, not just gravity, is calling the shots.
So then how do those electric currents actually form galaxies according to this model?
So imagine this. Instead of just gravity, right?
Yeah.
There are these immense currents, like cosmic rivers of electricity,
Wow.
shaping entire galaxies. We call them Birkeland currents.
Birkeland currents, got it.
And they're mind-blowingly huge. Think auroras, but on a scale that dwarfs our solar system.
Oh.
These currents flowing through the plasma, they generate their own magnetic fields. And these fields, in turn, influence the movement of more plasma, creating this kind of like self-reinforcing feedback loop that can pull matter together into those grand spiral structures we see as galaxies.
So instead of gravity being this lone sculptor struggling to shape these grand structures, you have electricity coming in as a co-creator.
Exactly.
That's a very different way of looking at the universe, that's for sure.
It is.
But if we entertain this idea for a moment, what happens when we zoom in even further to the scale of individual stars?
Well, that's where things get really electrifying.
Okay.
Because according to this model, stars aren't just giant nuclear furnaces, they're more like points on a cosmic power grid.
Stars as points on a cosmic power grid. Now that's a concept I can get behind. But how does that even work? How do you get a star to light up using electricity?
Well, remember those Birkeland currents we were talking about?
Mm.
Those massive currents shaping entire galaxies?
Yeah.
Well, imagine them flowing through a cloud of gas and dust. Now, under the right conditions, these currents can get incredibly focused. Like they squeeze the plasma with so much force that it heats up to extreme temperatures.
So you're saying it's like a giant cosmic pinch,
Yeah.
and boom, a star is born.
Exactly. And this model explains why stars often form in clusters. They're strung along those currents like beads on a wire.
Makes sense.
It's not random, it's following the path of these electric circuits.
That's really cool. And it makes those images we've seen of star-forming regions with those glowing filaments of gas and dust, it makes them even more incredible.
Absolutely. It's like looking at the blueprint of star formation in action. And even better, the electric universe model might be able to explain some recent observations about how young stars behave. Observations that have been kind of puzzling, actually.
Oh, really? Like what?
Well, astronomers have been studying these young stars in the Orion Nebula, right?
Right.
And they've noticed something strange. These baby stars, they seem to be fluctuating in brightness much faster than traditional models would predict.
Like they're flickering.
Exactly. And this kind of rapid variability, it's a lot easier to explain if stars are powered by an external electric current rather than just slowly burning their own fuel.
Oh, interesting. Okay.
It's like they're still finding their place in the galactic circuit. Their brightness changes as the current fluctuates around them.
Okay. I think I'm starting to see how this all fits together. We've gone from the vast scale of galaxies to the birth of individual stars. And electricity seems to be playing a key role every step of the way. But what about our own star, the sun? What does the electric universe have to say about that?
That's a great question, and it leads us to one of the most fascinating aspects of this model. You see, if the electric universe is correct, then the sun isn't just a ball of gas burning itself out in isolation.
It's plugged into this larger galactic circuit we've been talking about.
Exactly. And that has some pretty big implications. For example, remember when Voyager 1 crossed the heliosphere?
Yeah, wasn't that the first human-made object to reach interstellar space?
That's right.
It was a huge deal.
Huge. And scientists were expecting Voyager 1 to encounter a kind of shock front as it crossed that boundary. You know, a region of intense turbulence where the solar wind, that stream of charged particles from the sun, slams into the interstellar medium.
Right. That makes sense. So was there a shock front?
That's the thing, there wasn't. At least not the kind they were expecting. Instead, what they found was a much smoother transition, with a gradual increase in the density of the interstellar medium. And even more intriguing, Voyager 1 detected a significant increase in the intensity of high-energy electrons coming from outside the solar system.
Wait, so instead of a solar wind blowing outward, it's almost like the sun is drawing in energy from its surroundings, like a giant electrical sponge.
That's a great analogy. And that's exactly what the electric universe model would predict. You see, instead of a star's magnetic field creating a kind of hard edge to the solar system, it forms what's called a virtual cathode.
Virtual cathode. Okay, you're going to have to break that one down for me.
Sure. It's actually not as complicated as it sounds. Basically, it's a region where the electric potential is higher than in the surrounding space. Think of it like a buffer zone, between the star's own electrical field and the currents flowing through the galaxy.
So it's like the sun has its own electrical bubble, but it's constantly interacting with and even drawing energy from its surroundings.
Exactly. And this idea of the sun being electrically connected to the galaxy has some pretty big implications for how we understand things like solar flares, coronal mass ejections, even potentially the sun's long-term cycles. But that, my friend, is a deep dive for another day.
Okay, I am officially blown away. We've got galaxies sculpted by electricity, stars lighting up like cosmic Christmas lights,
Yeah.
and a sun that's more like a plugged-in powerhouse than just a boring old furnace.
Right.
It's a lot to take in.
It really challenges our conventional view of the cosmos. It really does. And, it makes you wonder, what are the implications for life itself?
Right. If this whole electric universe model is correct, and energy can flow between stars and galaxies like this,
Yeah.
maybe life out there isn't just looking for, like, habitable planets. Maybe they're looking for habitable circuits within the galaxy's power grid.
Exactly. It's a whole new way of thinking about the search for extraterrestrial intelligence. What if civilizations, at least the technologically advanced ones, cluster around these cosmic power lines, tapping into the universe's energy flow in ways that, we
Yeah.
can't even imagine?
It's mind-blowing. It really is. And it makes you wonder what humanity could achieve if we could unlock the secrets of this electric universe, you know?
Oh, yeah. Imagine harnessing the power of those Birkeland currents, traveling between stars on like streams of plasma. It sounds like science fiction, but in the electric universe, even the most, outlandish ideas suddenly seem within reach.
It's true. It makes you realize how much we still don't know about the universe.
100%.
We've been looking at it through the lens of gravity for centuries, and now this whole other layer, this electric layer, is starting to reveal itself.
Yeah.
It's exciting, it's challenging, and it's definitely a reminder that the cosmos is full of surprises.
It definitely is. And whether or not the electric universe model turns out to be the complete picture,
Right.
it's forcing us to ask new questions, to look at old data in a new light, and to be open to the possibility that our universe is even more fascinating and complex than we ever dreamed.
Well said. And that wraps up our deep dive into the electric universe. It's a topic that definitely sparks the imagination and leaves us with more questions than answers. But hey, that's what makes exploring the cosmos so much fun, right?
Absolutely.
Until next time, keep looking up and keep those questions coming.